Hello, friend. Welcome to another quiet journey through the cosmos. I'm glad you're here. Some nights when the world feels too loud, we look up. Stars breathe slower there. Time folds in on itself. And somewhere, 26,000 light years away, something watches back. Not with eyes, not with intent, but with gravity so deep, even light cannot climb out. At the center of our galaxy, there sits a monster made of darkness. And recently, humanity's most powerful telescope saw something it wasn't supposed to see, something strange, something that whispers of physics we don't yet understand. Tonight, we're going to drift toward that darkness together, gently, quietly. Let the questions do the heavy lifting. Before we begin, if you find comfort in these slow journeys through science, you might like to stay a while. You can gently tap the like button if this feels like home. Subscribe if you'd like more stories told softly. And ring that little bell not for noise, but so the next quiet night can find you again when you need it most. No pressure, just an invitation. Now, let's drift. Tonight we're traveling to the heart of the Milky Way, a place called Sagittarius A star. A supermassive black hole that weighs 4 million times more than our sun, yet makes no sound. For decades we've known it was there. We've watched stars dance around it like moths circling a flame they cannot see. But in the last few years, something changed. The James Webb Space Telescope turned its golden mirror toward that silent center. And what it found doesn't quite fit the story we've been telling ourselves. It saw light where there should be only shadow, flickers, pulses, eruptions of energy that appear, then vanish like breaths, taken by something vast and hidden. You don't need to understand everything tonight. Just rest. Let curiosity do the listening, because sometimes the most profound truths are the ones we feel before we know. Scientists suggest that black holes are not truly black. They're surrounded by disks of superheated gas spiraling inward at nearly the speed of light. This gas glows. It screams in X-rays and radio waves. But Sagittarius A star has always been quiet, strangely quiet. Compared to other supermassive black holes in distant galaxies, ours barely whispers. It's like a dragon that forgot how to breathe fire. Most of the time, it sleeps. And yet, Webb saw flashes, brief moments when the heart of our galaxy flared brighter, hotter, stranger than expected. Research shows these flares come in wavelengths our eyes could never see. Infrared light, heat signatures buried beneath clouds of cosmic dust. For billions of years, that dust has hidden the galactic center from us. Hubble couldn't pierce it. Ground-based telescopes saw only fog. But Webb was built differently. Its mirrors see in infrared the light of warmth and memory. It looks not at what shines, but at what glows quietly in the aftermath. And there in the glow, it found rhythms, patterns, as if something were breathing. Some believe these flares are caused by hotspots in the accretion disk regions, where magnetic fields twist and snap, releasing energy in bursts. Others think they might be the final cries of stars or planets torn apart as they cross too close to the event horizon, that invisible edge beyond which nothing, not even light, returns. It seems as though the black hole is not eating constantly, but in pulses, like a heart that beats only once every few hours, slow, patient, relentless. Imagine standing on a shoreline at night. The ocean is calm. Then without warning, a single wave rises, crashes, and retreats into silence. You wait. Minutes pass, then another wave. Not random, not constant. Just rhythmic enough to make you wonder if something beneath the surface is listening. That's what Webb detected. Quasi-periodic eruptions. Events that repeat but not like clockwork, more like breath. Irregular but alive. The black hole itself is invisible. We cannot see it. We never will. What we see is the echo of its hunger, the glow of matter falling inward, heating to millions of degrees as it spirals down into forever. Atoms stripped of their electrons, time stretching thin near the event horizon. And somewhere in that chaos, Webb's instruments picked up something unexpected, a structure, a shape in the infrared light, not solid, but present, like a shadow cast by something we cannot name. Here's what makes this strange Sagittarius A star sits at the gravitational center of 200 billion stars. Every star in our galaxy, including our sun, orbits this dark heart. It has been there since the Milky Way was young, perhaps even before. Some theories suggest supermassive black holes like this one are the seeds around which galaxies form. Gravity pulls gas and dust inward, stars ignite, spiral arms unfurl. And at the center, quiet and patient, the black hole waits. But waiting is not the same as stillness. In 2020, astronomers Andrea Ghez and Reinhard Genzel won the Nobel Prize in Physics for tracking stars near Sagittarius A star. For decades, they watched a star called S2 complete a full orbit around the black hole. It took 16 years. At its closest approach, S2 was traveling at nearly 3% the speed of light. 3%. That's roughly 20 million miles per hour. And even at that speed, even with all that kinetic fury, the star did not escape. Gravity held it, bent its path, pulled it back into another endless loop. General relativity predicted this. Einstein's equations described how massive objects warp space-time, how gravity is not a force pulling things together, but a curve in the fabric of reality itself. Near Sagittarius, A-star space-time is so warped that clocks tick slower. Light shifts red as it climbs out of the gravitational well. If you could somehow stand near the event horizon and look back at Earth, you would see billions of years pass in what felt like moments. Time, like light, bends. And yet, for all this violence, for all this cosmic drama, Sagittarius A-star remains relatively calm. Other supermassive black holes, like the one at the center of the galaxy, M87, are ravenous. They swallow entire star systems. They shoot jets of plasma thousands of light years into space. They glow so brightly we can see them across the universe. But ours is quiet. It eats, yes, but sparingly, like something conserving strength, or perhaps something already full. So, when Webb saw those flares, those strange pulses of infrared light, scientists paused. Because the data didn't match the silence, it suggested something new was happening. Maybe a cloud of gas had drifted too close. Maybe a star unseen and unfortunate had crossed the boundary and was being shredded by tidal forces, its atoms stretched into long threads of light before vanishing. Or maybe we were witnessing something even stranger. Magnetic reconnection events. Sudden snaps in the twisted magnetic fields that thread through the accretion disk, releasing energy in bursts like solar flares, but a billion times more powerful. There's a certain comfort in not knowing, a kind of peace in sitting with mystery rather than rushing to answer it. Webb's discovery is not a conclusion, it's an opening, a doorway into questions we didn't know we could ask. What causes these flares? How often do they happen? And what do they tell us about the nature of black holes, of space-time, of the universe itself? You might wonder why this matters, why we spend billions of dollars building telescopes to stare at something we can never touch, never visit, never truly see. And the answer, I think, is simpler than it seems. We look because we are human, because curiosity is woven into us as deeply as gravity is woven into space. Because every time we point a telescope at the sky, we are asking the same question our ancestors asked when they looked up at the stars and wondered what they were. We are asking, what is this place and what does it mean that we are here briefly to witness it? Sagittarius A star is not just a black hole. It is the anchor of our galaxy, the point around which everything we know revolves, every constellation, every nebula, every planet where life might exist, all of it orbiting this dark heart. And now, thanks to Webb, we know that heart is not as silent as we thought. It flickers, it breathes, it reminds us that even in the deepest darkness there is light we haven't yet learned to see. So, Tonight, as you drift towards sleep, carry this with you somewhere far beyond the edge of human sight. At the center of 100 billion stars, something ancient and patient is glowing, not constantly, not predictably, but steadily enough that we noticed, steadily enough that we cared. And in noticing and caring, we became part of the story, not separate from the cosmos, not observers watching from the outside, but threads woven into the same fabric, made of the same stardust, pulled by the same gravity. The universe is vast, but it is not indifferent. It hides things. Then slowly it reveals them. Light born from darkness, knowledge born from wonder, and all of it unfolding in the quietest hours when we finally stop asking and simply listen. But the black hole is only the beginning, because to understand what Webb saw, we first need to understand what a supermassive black hole truly is. Not just in equations or theory, but in the raw physical reality of space-time bent beyond recognition. We need to meet the silent monster that anchors our galaxy. And we need to see why, for something so massive, so violent, so utterly destructive, Sagittarius A star has spent most of its existence doing something unexpected, resting. A black hole doesn't announce itself. It doesn't glow. It doesn't hum. It simply is. And in being, it bends everything around it so profoundly that the universe itself warps in its presence. At the heart of our galaxy sits one such void. Sagittarius A star, a monster 4 million times the mass of our sun, compressed into a space smaller than Mercury's orbit. And for most of human history, we had no idea it was there. The term black hole itself wasn't coined until 1967 by physicist John Wheeler. Before that, they were called frozen stars or dark stars. Theoretical objects so dense that nothing could escape them. Albert Einstein's equations predicted their existence in 1915, but even Einstein doubted they could be real. He thought nature would find a way to prevent such extremes. He was wrong. Nature not only allows black holes, it seems to favor them. Nearly every galaxy we've observed contains a supermassive black hole at its center. Ours is no exception. But how do you find something that emits no light? How do you prove the existence of an object defined by absence? The answer lies not in seeing the black hole itself, but in watching what it does to everything around it. Scientists suggest that matter falling toward a black hole doesn't simply vanish quietly. It screams. As gas and dust spiral inward, they accelerate. Friction heats them. Atoms collide at relativistic speeds, stripping electrons and releasing radiation across the electromagnetic spectrum. X-rays, radio waves, gamma rays. The black hole remains invisible, but its appetite leaves evidence. In the 1970s, astronomers began detecting intense radio emissions from the center of the Milky Way. The source was compact, unmoving, and incredibly bright in radio wavelengths. They called it Sagittarius A, after the constellation where it appeared. Later observations revealed something even stranger. A cluster of stars near the galactic center were moving at impossible speeds, tracing elliptical orbits around what seemed to be nothing. One star, designated S2, completes a full orbit in just 16 years. To move that fast, it must be orbiting something with a mass equivalent to 4 million suns. Yet when astronomers pointed their telescopes at the center of that orbit, they saw only darkness. This is where patience becomes a scientific tool. Andrea Ghez, working at UCLA, and Reinhard Genzel, working in Germany, spent nearly 3 decades tracking these stars, frame by frame, year by year. They mapped the orbits with such precision that the invisible object's mass location and properties could be calculated with certainty. In 2020, they were awarded the Nobel Prize in Physics for proving beyond reasonable doubt that Sagittarius A star is a supermassive black hole, not a cluster of dark matter, not a dense swarm of neutron stars, a singularity, a point in space where matter has collapsed so completely that the laws of physics as we understand them break down. Research shows that supermassive black holes, like Sagittarius A star, likely formed in the early universe, perhaps, from the collapse of massive gas clouds or the merger of smaller black holes. Over billions of years, they grew, swallowing stars, gas, and anything else that wandered too close. But here's what makes our black hole peculiar. It's remarkably calm. Most supermassive black holes are surrounded by bright, roiling accretion disks, vast spirals of superheated matter glowing across millions of miles. Some shoot relativistic jets, beams of particles traveling at 99%, the speed of light extending thousands of light years into space. These are called active galactic nuclei, or AGN. They are among the brightest objects in the universe. Sagittarius A star is not one of them. It sits quietly. It flickers occasionally, yes, but compared to its cosmic cousins, it barely eats. Astronomers estimate that it captures less than 1% of the gas and dust available in the surrounding region. The rest simply drifts past, untouched. It's as if the black hole is full, or perhaps it's waiting. Some believe this quietness is temporary. There's evidence that Sagittarius A star was far more active in the recent past, cosmically speaking. In 2010, NASA's Fermi Gamma Ray Space Telescope discovered two massive bubbles of high-energy radiation extending above and below the galactic plane, each spanning about 25,000 light-years. These structures, now called the Fermi bubbles, are thought to be the remnants of a massive outburst from Sagittarius A star, possibly triggered by a sudden influx of matter several million years ago. The black hole awoke briefly, it fed, and then it went back to sleep. But even in sleep, it shapes everything. The gravitational pull of Sagittarius A star governs the motion of hundreds of billions of stars. Our sun, located 26,000 light-years from the galactic center, orbits this black hole once every 230 million years. We are quite literally circling the drain, slowly, inevitably, though not urgently. The sun will die long before it falls inward. Near the event horizon, reality becomes stranger still. Time dilates. If you could hover just outside the boundary of no return and watch the universe beyond you, would see stars aging and fast forward, galaxies colliding, the universe expanding, then contracting, then ending, all in what would feel to you like minutes. But to an outside observer, you would appear frozen, your light redshifted into invisibility, your motion slowed to an eternal stillness. This is what happens at the edge of a black hole. Time and space trade places, directions lose meaning, inward becomes inevitable. It seems as though the event horizon is not a physical surface, but a boundary in space-time itself. Cross it, and you cannot come back. Not because the black hole won't let you, but because every direction you could travel, every path through space-time now points inward. Escape is not forbidden. It is geometrically impossible, like trying to travel north from the North Pole. There is no north beyond that point, only south, only inward. And at the very center, hidden forever behind the event horizon, lies the singularity, a point of infinite density, or perhaps not a point at all, perhaps a ring as some rotating black hole models suggest, or perhaps something else entirely, something beyond the reach of general relativity, where quantum mechanics must take over. We don't know. We can't know. The singularity is cloaked by the event horizon, veiled by the universe's own laws. Some physicists call this cosmic censorship. Nature, it seems, does not allow naked singularities. It hides its infinities. But Sagittarius A star is not the only black hole in our galaxy. There are millions of smaller ones, remnants of massive stars, that collapsed at the end of their lives. These stellar mass black holes, typically between 5 and 20 times the mass of the Sun, are scattered throughout the Milky Way. Occasionally, they betray their presence by devouring a companion star, producing brilliant X-ray flares. But supermassive black holes are different. They are ancient, foundational, architects of galaxies. One puzzle that remains is how these supermassive black holes grew so large so quickly. Observations from the James Webb Space Telescope have revealed supermassive black holes in galaxies less than 1 billion years old, shortly after the Big Bang. How did they accumulate millions or billions of solar masses in such a short time? Some theories propose that they formed directly from the collapse of massive primordial gas clouds bypassing the stellar phase entirely. Others suggest rapid mergers and dense star clusters. The answer, like so much in astrophysics, is still unfolding. Here's a question to carry with you. If black holes are defined by what they take, by what they consume and hide, what does it mean that we can still study them? That we can infer their mass, their spin, their history? Perhaps it means that even the universe's deepest secrets leave traces, that nothing, not even a singularity, exists in total isolation. Everything is connected. Everything leaves a mark. Sagittarius A star weighs 4 million solar masses. To put that in perspective, if you could somehow gather all the planets in our solar system, all the asteroids, all the comets, all the dust, and compress them into a single point, you wouldn't even come close. You would need to add the sun, then add 4 million more suns. Only then would you approach the mass of our galactic black hole. And yet, despite this immensity, its event horizon is only about 17 times the diameter of our sun. 17 solar diameters, containing 4 million solar masses. Density beyond comprehension. The escape velocity at the event horizon is exactly the speed of light, 300,000 kilometers per second. Nothing with mass can reach that speed. Therefore, nothing with mass can escape. Photons which have no mass can travel at light speed, but even they, once they cross the boundary, cannot climb back out. They are trapped in space-time's one-way current. Scientists also suggest that black holes rotate, not as solid objects, but as swirling distortions in space-time itself. This rotation drags space-time around, with it a phenomenon called frame dragging, or the lens-thirring effect. Near a rotating black hole, space itself is pulled in the direction of the spin. It's not that objects are being pushed, it's that the very coordinate system, the grid of reality, is turning. You could fire a rocket perpendicular to the black hole's rotation and watch it curve, not because of gravity alone, but because the space through which it travels is itself rotating. Sagittarius A star is believed to be rotating, though measuring its spin precisely is difficult. The faster a black hole spins, the closer its innermost stable orbit gets to the event horizon. For a non-rotating black hole, the closest stable orbit is 3 times the radius of the event horizon. For a maximally rotating black hole, it shrinks to just half that distance. Matter can orbit closer, heat up, more, shine brighter. If Sagittarius A star spins rapidly, its accretion disk would be smaller, hotter, and more energetic than if it were stationary. And yet, with all this complexity, all this violence encoded in curved space-time, Sagittarius A star remains difficult to observe. It sits behind 26,000 light-years of gas and dust. Visible light cannot penetrate that veil. For decades, astronomers relied on radio and infrared observations. They built larger telescopes. They combined signals from observatories across the planet, creating a virtual telescope the size of Earth. This is how, in 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star. Not a photograph, but a reconstruction, a shadow. The absence of light ringed by the glowing accretion disk. That image confirmed what mathematics had predicted. The black hole is real. Its event horizon is there exactly where Einstein's equations said it would be. And the universe once again proves stranger and more precise than fiction. But knowing the black hole exists is only the first step. The real question, the one that pulls us deeper, is this: why does such a massive object remain so quiet? And what happened recently to disturb that silence? Because the flickers Webb detected those strange infrared pulses suggest something is changing. Something is stirring in the dark. To understand that, we need to understand the tool that saw it. We need to meet the telescope that can see heat through dust, memory through shadow, and light born a billion years ago. We need to understand the eye humanity built to see the invisible. Imagine trying to see through a wall of fog, not thin mist, but dense ancient cloud, stretched across thousands of light years. For centuries, that's what separated us from the center of our galaxy. Visible light, the kind our eyes detect, cannot pass through cosmic dust. It scatters, it fades. The galactic core remained hidden, a mystery wrapped in darkness. Then, on December 25th, 2021, humanity launched an eye designed to see what darkness hides, the James Webb Space Telescope. And with it, everything changed. Webb doesn't see like we do. It doesn't look for blue skies or red sunsets. It sees heat, infrared light, the glow of things cooling, fading, remembering. It's an instrument built not to observe the present, but to witness the past. Because light takes time to travel. When Webb looks at distant galaxies, it's seeing them as they were billions of years ago, their light only now reaching us. When it turns toward the galactic center, it peers through the veil that has hidden Sagittarius A star from human eyes, since we first looked up and wondered what those stars were. The idea for Webb began in the mid-1990s, shortly after the Hubble Space Telescope revolutionized astronomy. Hubble showed us galaxies in visible light, stunning images of star birth and cosmic architecture. But Hubble had limits. It couldn't see through dust. It couldn't detect the faint infrared glow of the universe's earliest stars. So, NASA, along with the European Space Agency and the Canadian Space Agency, began planning a successor, not a replacement, but a complement, a telescope designed to see what Hubble couldn't. They called it the Next Generation Space Telescope at first. Later, it was renamed after James E. Webb, the NASA administrator who led the agency during the Apollo era. The design was audacious. A mirror 6.5 meters across, made of 18 hexagonal segments coated in gold. Gold reflects infrared light better than almost any other material. Each segment had to be polished to within a millionth of an inch, then aligned in space with such precision that the entire mirror functions as a single flawless surface. Engineers called it perfect enough to see a bumblebee at the distance of the moon. Research shows that building Webb required solving problems no one had faced before. The telescope would orbit nearly 1,000,000 miles from Earth, far beyond the reach of repair missions. Everything had to work the first time. The mirror had to unfold in space. The sun shield, a 5-layer barrier the size of a tennis court, had to deploy without tearing. And the instruments had to cool to just a few degrees above absolute zero, cold enough that their own heat wouldn't interfere with the faint infrared signals they were designed to detect. The project took 30 years and cost roughly $10 billion. There were delays, budget overruns, congressional hearings where politicians questioned whether it was worth the expense. Some called it a waste. Others called it humanity's best chance to answer fundamental questions. How did the first galaxies form? Are there planets like Earth around other stars? What lies hidden in the hearts of galaxies like our own? In the end, science won. Webb launched on Christmas Day 2021 atop an Ariane 5 rocket from French Guiana, and for 29 days the world held its breath. Webb had to execute one of the most complex deployment sequences ever attempted in space, over 300 single-point failures. Any one of them could have ended the mission. The sun shield had to unfold in stages, each layer separated by gaps to allow heat to radiate into space. The mirror segments folded for launch had to swing into position and lock. The secondary mirror, suspended on a tripod boom, had to extend. Then over weeks, engineers on the ground adjusted each of the 18 primary mirror segments, tweaking their positions with nanometer precision until they focused together as one. Scientists suggest that the moment Webb's mirror aligned perfectly was one of the most technically demanding achievements in the history of spaceflight. The telescope was designed to observe wavelengths from zero point 0.6 microns near the edge of visible red light all the way to 28 microns deep in the infrared. Human eyes can't see infrared, but cameras cooled to minus 230 degrees Celsius can. And what they see is extraordinary. Infrared light passes through dust that blocks visible light. This means Webb can observe star-forming regions inside nebulae, where new suns ignite hidden within cocoons of gas. It can peer into the cores of distant galaxies, seeing the black holes at their centers, even when surrounded by thick clouds of material. And it can look at the galactic center 26,000 light-years away and detect structures that Hubble could never resolve. One of Webb's first targets was the galactic core. Astronomers pointed its near-infrared camera, or NIRCam, at the region surrounding Sagittarius A star. What they found was not the empty darkness they might have expected, but a landscape. Filaments of hot gas, clusters of young stars, some only a few million years old, impossibly close to the black hole. Dense knots of matter glowing faintly in wavelengths, invisible to the naked eye. And within that glow patterns, variations in brightness, flickering like embers breathing in a dying fire. It seems as though Webb had captured something Hubble never could: the accretion disk itself, or at least its outer edges. The superheated gas spiraling toward the event horizon emits strongly in infrared. As clumps of matter orbit the black hole, they heat unevenly, creating bright spots that rotate with the disk. These hotspots can explain some of the variability astronomers observe, but not all of it. Some flares are too bright, too brief, too energetic to come from the steady churn of the accretion disk alone. Webb's instruments work by collecting infrared photons and measuring their wavelengths with extreme precision. Different molecules and elements emit light at specific infrared frequencies. By analyzing the spectrum, scientists can determine what the glowing material is made of. Near Sagittarius, A star Webb detected signatures of ionized gas, hydrogen, helium, and heavier elements. This tells us the black hole is feeding on material enriched by previous generations of stars' gas that has been cycled through stellar furnaces and returned to space. One of Webb's most powerful features is its ability to observe simultaneously in multiple infrared bands. This allows astronomers to compare how an object appears at different wavelengths, revealing details invisible in any single image. When they did this for Sagittarius A star, they found that certain features appeared brighter in some wavelengths than others, suggesting complex physical processes at work. Magnetic fields, shock waves, turbulence in the gas. But Webb's contribution goes beyond imaging. It also uses spectroscopy to measure motion. By examining how light is redshifted or blue-shifted, astronomers can determine whether gas is moving toward us or away from us, and how fast. Near the black hole, some gas is moving at thousands of kilometers per second, whipped into frenzy by gravity and magnetic forces. Other gas drifts more slowly, perhaps falling inward in a more stable circular orbit. This velocity data helps scientists build models of how matter behaves in the extreme environment near the event horizon. Here's something to consider. Webb is located at a point in space called the second Lagrange point, or L2. It's a gravitationally stable location where the pull of the sun and the pull of the Earth balance perfectly, allowing the telescope to orbit the sun while staying aligned with Earth. This position keeps Webb in perpetual shadow, shielded from the sun's heat by its enormous sun shield. The side facing the sun reaches temperatures of about 85 degrees Celsius. The side facing away where the instruments sit stays colder than liquid nitrogen. This temperature difference is essential. Infrared observations require cold detectors. Any warmth would create noise, drowning out the faint signals from distant stars and galaxies. Some believe Webb represents a turning point in astronomy, comparable to Galileo's first use of the telescope in 1609. Just as Galileo saw moons orbiting Jupiter and proved that not everything revolves around Earth, Webb is showing us galaxies forming in the universe's infancy exoplanet atmospheres, with biosignatures and black holes behaving in ways we didn't anticipate. It's not just a better telescope, it's a different kind of seeing. When Hubble looked at the galactic center, it saw stars, but the region appeared crowded, chaotic, difficult to interpret. Webb, with its infrared vision and sharper resolution, can distinguish individual stars even in the densest clusters. It can watch them move over time, refining our measurements of the black hole's mass and position. And it can detect faint, cool objects that emit little visible light but glow brightly in infrared. Brown dwarfs, planetary mass objects, dust clouds heated by starlight. One discovery that surprised scientists was how young some of the stars near Sagittarius A star appear to be. Stars form from collapsing clouds of gas and dust, a process that should be disrupted by the black hole's gravity. Yet there they are, massive young stars orbiting within light years of the event horizon. Some theories propose they formed farther out and migrated inward. Others suggest they formed in a disk of material around the black hole itself, similar to how planets form around stars. Webb's observations are helping to test these ideas, measuring the stars' compositions and ages with unprecedented detail. Webb also excels at observing transient events phenomena that change over hours or days. When Sagittarius A star flares, Webb can capture the event in real time, recording how the brightness changes across multiple infrared wavelengths. This data is crucial for understanding what triggers the flares. Is it a magnetic reconnection event, like a solar flare, but millions of times more powerful? Is it a clump of gas suddenly heating as it crosses into the innermost regions of the accretion disk? Or is it something else, something we haven't yet imagined? Research shows that Webb's mirrors are so finely tuned that they can detect objects 100 times fainter than Hubble could. This sensitivity allows astronomers to study not just the brightest phenomena, but the subtle, quiet processes that unfold slowly over cosmic time scales. Near Sagittarius A star, there are structures that pulse gently, brightening and dimming over weeks. These could be shock fronts moving through the accretion disk or spiral density waves, similar to the arms of a galaxy, but on a much smaller scale. There's a kind of poetry in Webb's construction. It was built by thousands of engineers, scientists, and technicians across multiple continents, people who will never visit space themselves, but who devoted decades to ensuring that this telescope could. And now, from a million miles away, it sends back data photons that travel 26,000 years through the galaxy, captured by gold mirrors, converted to electrical signals, transmitted to Earth, and translated into images we can study. Each picture is a collaboration between human ingenuity and the patience of light. One challenge Webb faces is managing the sheer volume of data it collects. The telescope generates terabytes of information every day. Astronomers must sift through it, identifying interesting signals, filtering out noise, and piecing together narratives from pixels and spectra. It's painstaking work, but within that data are answers, clues to how galaxies evolve, how stars die, how black holes grow, and perhaps hidden in the infrared glow near Sagittarius A star, clues to what Webb saw that no one expected. Because seeing through the dust was only the first step. Detecting the flare was the second. Now comes the question that pulls us deeper. What exactly did Webb find? What pattern emerged from the noise? What light? What heat? What whisper from the edge of the event horizon made scientists pause and say, "That's not supposed to happen"? The answer lies not in the telescope, but in the data it returned. Strange, persistent, undeniable. Data doesn't lie, but it whispers. And in the spring of 2023, Webb's infrared detectors began picking up something unusual. Not a steady glow, not random noise, but a pattern, a rhythm. Pulses of infrared light emanating from the region, immediately surrounding Sagittarius, A star appearing and fading like the slow blink of an eye opening in the dark. The flares lasted minutes, sometimes hours. Then they vanished. And just when astronomers thought they understood the tempo it changed, scientists suggest that what Webb detected are known as quasi-periodic eruptions, or QPEs. The term sounds technical, clinical even, but it describes something profoundly strange. These are bursts of energy that repeat, but not like a clock, more like breathing. Irregular rhythms that suggest something alive, something responding to forces we can't yet see. The infrared signature peaked, then declined only to rise again hours later. Sometimes the interval was 3 hours, sometimes 6. Sometimes the pattern broke entirely, leaving only silence. Research shows that QPEs were first discovered in X-ray observations of distant galaxies in 2019. Astronomers using the European Space Agency's XMM Newton telescope noticed that certain supermassive black holes were emitting X-ray flares in repeating patterns. The discovery was surprising because most black hole activity appears chaotic. Accretion disks churn, matter falls inward unpredictably. There's turbulence, friction, magnetic chaos. But QPS suggested something different: structure, periodicity, as if the black hole's feeding habits were governed by an underlying order. Webb's detection of similar patterns in infrared wavelengths near Sagittarius A star marked the first time such eruptions were observed at the center of our own galaxy. The timing mattered. Infrared light reveals heat, the thermal afterglow of violent processes. When gas near a black hole heats to millions of degrees, it emits X-rays. But as that gas expands and cools, it glows in infrared. What Webb saw was likely the echo, the memory of something hotter and brighter that had already passed. Let me offer an analogy. Imagine standing near a fireplace that's been burning all night. The flames die down. The wood turns to embers. But hours later, if you hold your hand near the hearth, you still feel warmth radiating from the stones. That warmth is infrared radiation, heat stored and slowly released. Webb detected something similar near Sagittarius A star. The violent event, whatever it was, had already occurred. What remained was the glow. One leading theory is that these eruptions are caused by hot spots in the accretion disk. As gas spirals toward the black hole, it doesn't fall smoothly. Instabilities form. Magnetic fields twist and compress pockets of gas, heating them to extreme temperatures. These hotspots orbit the black hole, moving at a significant fraction of light speed. Each time a hotspot swings into our line of sight, we see a brightening. Then it rotates away, and the brightness fades. If the disk is slightly warped or tilted, the interval between flares would vary exactly as Webb observed. But there's a complication. Hot spots should produce a regular pattern, like the beam of a lighthouse sweeping past. Webb's data showed irregularity. The flares didn't repeat like clockwork. Some were brighter than others. Some lasted longer. Some appeared in clusters, 3 or 4 in quick succession, followed by long periods of quiet. This suggests the hotspots themselves are changing, evolving, or that multiple processes are happening simultaneously. Another possibility is magnetic reconnection. In the disk surrounding Sagittarius, A-star magnetic field lines are stretched and twisted by the motion of ionized gas. Sometimes these field lines snap, reconnecting in a different configuration and releasing enormous amounts of stored energy in an instant. This is similar to what happens during solar flares on the sun, but scaled up by a factor of billions. A single reconnection event near a supermassive black hole can release as much energy as our sun produces in a year. Scientists suggest that reconnection events are inherently unpredictable. They depend on the tangled geometry of magnetic fields, which change constantly as gas flows, and turbulence churns the disk. This unpredictability matches what Webb observed. The flares come when conditions align, when the magnetic tension reaches a breaking point. Then they release. And then the system resets, building tension until the next snap. There's also the possibility, uncomfortable but necessary, to consider that Webb witnessed tidal disruption events. These occur when a star or planet wanders too close to the black hole and is torn apart by tidal forces. The side of the object facing the black hole experiences stronger gravity than the side facing away. This difference stretches the object into a long filament of plasma, which then spirals inward, heating and glowing as it falls. Tidal disruption events are catastrophic, bright, violent, and they produce flares that can last days or weeks, as the debris settles into an accretion disk. However, tidal disruption events are relatively rare. Astronomers estimate they happen once every 10,000 to 100,000 years per galaxy. The fact that Webb detected multiple flares over a short observation period suggests something more common is at work, unless, of course, we're witnessing an exceptionally active phase. Perhaps a cluster of smaller objects, asteroids or comets, is passing near Sagittarius A star, each one meeting its end in a brief flash of infrared light. Here's where the data becomes truly intriguing. Webb didn't just detect brightness changes. It recorded spectroscopic data measuring the exact wavelengths of the infrared light. Different elements and molecules emit light at characteristic wavelengths, creating a fingerprint that reveals what the glowing material is made of. Near Sagittarius A star, Webb detected emission lines consistent with ionized hydrogen, helium, and traces of heavier elements like carbon and oxygen. This composition matches what we'd expect from stellar material gas that has been processed inside stars and returned to space through supernovae or stellar winds. But there was something else, a faint emission line that didn't quite match known elements. Scientists are still analyzing it, checking against databases of atomic and molecular spectra. It could be an exotic ionization in state, atoms stripped of so many electrons that they emit at unusual wavelengths. Or it could be a Doppler-shifted line light from gas moving at relativistic speeds so fast that the wavelength is stretched or compressed. Either way, it's a clue, a detail that doesn't fit neatly into existing models. Some believe the infrared flares are connected to X-ray flares detected by other observatories. NASA's Chandra X-ray Observatory and the Swift satellite have both observed sudden brightening episodes from Sagittarius A star, sometimes lasting just a few minutes. When astronomers compared the timing of X-ray flares with Webb's infrared detections, they found a correlation, though not a perfect one. Some infrared flares appeared hours after an X-ray event, suggesting they were the cooling phase of the same process. Other infrared flares had no corresponding X-ray counterpart, hinting at multiple mechanisms at play. One detailed study published in 2024 combined data from Webb Chandra and the Atacama Large Millimeter Array, or ALMA, a radio telescope in Chile. By observing Sagittarius A star simultaneously across multiple wavelengths, astronomers could track how energy propagates through the system. They found that X-ray flares occur first, followed by infrared peaks, and finally, hours later, radio brightening. This sequence suggests a cooling cascade. The initial event heats gas to X-ray emitting temperatures. As it expands and cools, it transitions to infrared. Eventually, it cools further, becoming visible in radio wavelengths as synchrotron radiation from electrons spiraling through magnetic fields. It seems as though the black hole is not a static object, but a dynamic system with layers and processes unfolding across time and space. What we call Sagittarius A star is not just the singularity at the center, but the entire ecosystem surrounding it. The event horizon, the accretion disk, the corona of hot plasma above and below the disk, the magnetic field lines threading through it all, and perhaps orbiting just beyond the point of no return, dense clumps of matter waiting their turn to fall inward. One question astronomers are asking is whether these flares are a new phenomenon or something we simply couldn't detect before. Sagittarius A star has been observed for decades, but mostly in radio wavelengths and lower resolution infrared. Webb's sensitivity and precision are unprecedented. It's possible these eruptions have been happening all along, and we're only now seeing them clearly. Or it's possible something has changed. Perhaps the black hole recently captured a new source of material, triggering an active phase that will last years or centuries before settling back into quiescence. There's also the intriguing possibility that the flares are precursors to something larger. In some galactic nuclei, periods of increased activity lead to full-blown outbursts where the black hole awakens and begins feeding voraciously. If Sagittarius A star is transitioning from a dormant state to an active one, we might be witnessing the early stages. Over the next decades, the flares could grow stronger, more frequent, until the galactic center blazes with light across all wavelengths. But predictions are difficult. Black holes operate on timescales both faster and slower than human perception. A flare lasting hours is instantaneous on cosmic scales. Yet the underlying processes, the slow inward migration of gas, the gradual buildup of magnetic tension, unfold over thousands of years. We see snapshots, moments, and from those moments, we try to reconstruct the whole story. Consider this: every photon Webb detected traveled 26,000 years to reach us. The flare we're observing now happened during the Stone Age on Earth. Our ancestors were painting on cave walls, making tools from stone, telling stories around fires. They had no idea that far above them, light was already journeying through space, carrying information about a black hole's fleeting breath. And now, in 2023, that light arrived. It struck gold-coated mirrors. It was focused, analyzed, recorded, and we, the descendants of those cave painters, are reading its message. What does the message say? That's the challenge. Data is not meaning. It's raw information, numbers in a spreadsheet, spectra on a graph. Scientists must interpret it, building models, testing hypotheses, arguing over details in conference rooms and email threads. Some models suggest the flares will continue, perhaps even intensify. Others predict they'll fade as the current supply of infalling material is exhausted. The truth, as always, will emerge slowly through careful observation and patient analysis. One thing is certain: Webb has given us a new way to listen to the galactic center, not with our ears, but with instruments sensitive enough to hear whispers across 26,000 light years. And those whispers are telling us that Sagittarius A star, for all its silence, is not inactive. It's restless, breathing, flickering at the edge of waking. And if we watch closely enough, we might see what happens when it fully opens its eyes. But the flares are only part of the puzzle. To truly understand what's happening, we need to zoom in closer to the region immediately surrounding the event horizon. We need to meet the stars that orbit so close to the black hole they experience time differently than we do. Stars moving so fast, they blur the line between matter and energy. Stars dancing on the edge of oblivion, teaching us about gravity in ways no laboratory ever could. There are places in the universe where physics becomes performance, where gravity choreographs motion so extreme that watching it tests the limits of what we thought possible. Near Sagittarius A star, a handful of stars have been locked in orbit so tight, so fast, so impossibly close to the edge of forever, that observing them is like watching Einstein's equations come alive. These are the S stars, and their dance has rewritten our understanding of space-time itself. The first of these stars was discovered in the early 1990s. Astronomers using infrared telescopes noticed something peculiar: a bright point of light moving near the galactic center, not in a gentle arc like most stars, but in a sharp ellipse swinging close to the invisible mass at the center before racing back out into the relative safety of open space. They labeled it S1, then they found S2, then more. By the early 2000s, dozens of S stars had been cataloged, each one tracing its own chaotic path around the black hole. S2 became the most famous. It's a blue giant about 15 times the mass of the Sun, burning hot and bright enough to track with precision. Its orbit takes 16 years to complete. 16 years. That might sound slow, but consider this S2's closest approach to Sagittarius. A star brings it within just 17 light hours of the event horizon. 17 light hours. That's roughly the distance from the Sun to Uranus. Imagine our entire solar system out to Neptune, compressed into the space S2 crosses in a single orbit. And at that closest point, it's moving at nearly 5,000 kilometers per second, almost 2% the speed of light. Research shows that tracking S2 required decades of patience. Astronomers photographed the galactic center night after night, year after year, recording the star's position with painstaking accuracy. They used adaptive optics to correct for the blurring caused by Earth's atmosphere, sharpening the images until individual stars could be resolved even in the crowded core. Slowly, they built a map of S2's orbit. And what they found confirmed what Einstein had predicted a century earlier near massive objects' space-time warps. As S2 approached the black hole in 2018, scientists watched closely. General relativity predicts that light climbing out of a strong gravitational field loses energy, a phenomenon called gravitational redshift. The deeper the gravity well, the more the light stretches toward longer, redder wavelengths. Observations of S2 showed exactly this effect. The star's light analyzed with spectrographs was redshifted by precisely the amount Einstein's equations predicted. It was direct observational proof that space-time near Sagittarius, A star, behaves as general relativity describes. But S2 is not the fastest star in this cosmic ballet. That distinction belongs to S4714, discovered more recently and moving even closer to the black hole. Scientists suggest that S4714 reaches speeds of up to 8% the speed of light at its closest approach. 8%. That's 24,000 kilometers per second. Faster than anything with mass has a right to move. At that speed, relativistic effects become impossible to ignore. Time dilation, length contraction. The star experiences time differently than we do. If you could somehow stand on S4714 during its close pass, you would age slightly slower than someone watching from Earth. Not by much, but measurably so. The existence of these stars raises an obvious question. How did they get there? Stars form from collapsing clouds of gas, a process disrupted by strong tidal forces. Near a supermassive black hole, tidal forces are extreme. Gas clouds should be torn apart long before they can collapse into stars. So, how do we explain the S stars, massive and young, orbiting in a region where they shouldn't exist? One theory is that they formed farther out and migrated inward over millions of years. Gravitational interactions with other stars or with the black hole's accretion disk could have gradually nudged them closer. Another theory suggests they are the remnants of binary star systems. If two stars orbited each other and one ventured too close to Sagittarius, A star, the black hole's gravity could have captured one star while flinging the other away at high speed. The captured star would then settle into a tight orbit, becoming an S star. Some believe the S stars might have formed in a disk of gas and dust that once surrounded the black hole, similar to how planets form around stars. This disk would have been dense and stable enough to shield collapsing gas clouds from tidal disruption. Over time, as the disk dissipated, the stars at birth were left behind, locked in their extreme orbits. Evidence for this theory comes from the fact that many S stars orbit in roughly the same plane, suggesting they share a common origin. Whatever their history, the S stars are now living laboratories for extreme physics. By measuring their orbits with exquisite precision, astronomers can test predictions of general relativity that are impossible to verify anywhere else. One such prediction is orbital precession, the gradual rotation of an orbit's orientation over time. Newton's gravity predicts that orbits should be perfect, unchanging ellipses. But Einstein's theory predicts that in strong gravitational fields, orbits precess the ellipse itself, slowly rotating like a spinning coin settling on a table. Observations of S2 have confirmed this precession. Each time the star completes an orbit, its closest approach point shifts slightly, exactly as general relativity predicts. The effect is tiny, but measurable, and it's one more piece of evidence that Einstein was right. Gravity is not a force, it's the curvature of space-time. And near Sagittarius A star space-time is curved so sharply that even the paths of stars are bent into shapes Newton never imagined. Here's another layer of strangeness: the S stars are not alone in their orbits. Recent observations have detected fainter objects, possibly smaller stars, or even planetary mass bodies also orbiting the black hole. Some of these objects move in highly eccentric orbits, swinging close to the event horizon before retreating to safer distances. If any of these objects strays too close, they'll be torn apart by tidal forces in an event astronomers call spaghettification. The side facing the black hole will be pulled harder than the side facing away, stretching the object into a long, thin strand of plasma before it disappears across the event horizon. It seems as though the region around Sagittarius A star is more dynamic, more populated than we once thought. It's not an empty void with a black hole at the center. It's a crowded neighborhood full of stars, gas dust, and debris, all swirling in a gravitational maelstrom. And occasionally something crosses the line. A star ventures too close. A cloud of gas drifts inward, and the black hole feeds. Scientists also suggest that magnetic fields play a crucial role in this environment. Near the black hole, magnetic field lines are dragged and twisted by the motion of ionized gas. These fields can channel material, directing it toward the event horizon or flinging it outward in jets. The interaction between gravity and magnetism is complex, nonlinear, and still not fully understood. Simulations run on supercomputers attempt to model this interplay, but the equations are so difficult that even the most powerful machines struggle to solve them. One fascinating discovery came from studying the spectra of S stars. Astronomers found that some of these stars show unusual chemical compositions enriched in elements like helium and nitrogen. This suggests they may have undergone close interactions with other stars in the past, stripping away outer layers or accreting material from a companion. In the dense environment near the galactic center, stellar collisions and close encounters are far more common than in the quieter regions of the galaxy where our sun resides. There's also evidence that some S stars are pulsating variable stars whose brightness changes rhythmically as they expand and contract. These pulsations are driven by internal processes, layers of the star, alternately heating and cooling. By measuring the period of pulsation, astronomers can determine the star's intrinsic brightness. Comparing this to how bright it appears from Earth reveals its distance, providing an independent check on the black hole's position and mass. Have you ever wondered what it would be like to stand on a planet orbiting one of these S stars? Assuming such a planet could exist in such a hostile environment, the sky would be a spectacle beyond imagination. The black hole itself would be invisible, but its accretion disk would glow a thin ring of light encircling darkness. Stars would wheel overhead, at visible speeds, their positions shifting noticeably over the course of hours. And time itself would flow differently. Clocks on that planet would tick slower than clocks on Earth, a consequence of the intense gravitational field. Research shows that the study of S stars has also helped refine our measurement of the black hole's mass. By applying Kepler's laws of motion to the orbits of multiple stars, astronomers can calculate the mass of the object they're orbiting with remarkable precision. Current estimates place Sagittarius A star at approximately 4.1 million solar masses, with an uncertainty of less than 1%. That's an astonishing level of accuracy for something 26,000 light-years away. One unexpected finding was the discovery that the black hole's spin might be measurable through the precession of S-star orbits. A rotating black hole drags space-time around, with it an effect called frame dragging. This dragging influence would subtly alter the orbits of nearby stars in ways distinct from standard precession. By tracking S2 and other stars over multiple orbits, astronomers hope to detect this effect and determine how fast Sagittarius A star is spinning. Is it rotating rapidly near the maximum possible spin, or is it more sedate, turning slowly? The answer would tell us about the black hole's history, how it formed, and how it has grown over billions of years. There's also the intriguing possibility of detecting gravitational waves from the S stars. When objects orbit very close to a black hole, they emit gravitational waves, ripples in space-time, that propagate outward at the speed of light. These waves are incredibly faint, far below the sensitivity of current detectors, like LIGO, which are designed to detect waves from colliding black holes and neutron stars. But future space-based gravitational wave observatories like the planned LISA mission might be able to detect the persistent hum of gravitational radiation from S stars orbiting Sagittarius A star. One detail that often surprises people is just how empty space is even near the galactic center. The S stars are separated by vast distances. If you were on S2, the nearest other S star would still be light weeks or light months away, far too distant to see as anything but a faint point of light. Space does not become crowded just because gravity is strong. It becomes dangerous, but still mostly empty. Scientists suggest that over time, some S stars will be ejected from their orbits, flung out of the galactic center at high speed by gravitational interactions. These so-called hypervelocity stars have been detected elsewhere in the galaxy, moving so fast they're escaping the Milky Way entirely. They're refugees from the galactic core stars that danced too close to chaos and were thrown clear, destined to wander intergalactic space forever. Others less fortunate will spiral inward. Each orbit brings them slightly closer, as gravitational wave emission and interactions with gas slowly drain their orbital energy. Eventually, they'll cross the event horizon, and when they do, they won't explode. They won't flash. They'll simply vanish, their light redshifting into invisibility as they fall toward the singularity, adding their mass to the black hole's total. It's a quiet end. No fanfare. Just silence. The S stars teach us that the universe is not bound by human intuition. We think of orbits as stable, predictable, safe. But near a black hole, orbits are temporary arrangements, brief moments of balance in an environment defined by extremes. The stars are falling just slowly enough that we can watch. And in watching, we learn about gravity, about time, about the limits of matter and the resilience of space-time. But watching the S stars is only one piece of the puzzle. The flares. Webb detected the strange rhythms in the infrared, suggests something else is happening closer still to the event horizon. To understand those flares, we need to explore the theories, the competing explanations, the scientific debates about what drives this restless black hole to occasionally flicker and breathe. We need to ask not just what we've seen, but what it means. Science begins with a question, but sometimes the hardest part isn't finding the answer. It's deciding which question to ask first. When Webb detected those strange infrared flares near Sagittarius, A-star astronomers didn't rush to conclusions. They paused. They compared notes. They built models, ran simulations, argued in journals and conference halls. Because a flare from a black hole isn't just a flare, it's a clue, a whisper from a place where the laws of physics stretch thin. And understanding it requires weaving together threads from magnetism, relativity, thermodynamics, and perhaps physics we haven't yet discovered. The first theory, and perhaps the most elegant, centers on hotspots in the accretion disk. Picture the disk as a vast spiral of gas, dust, and plasma, orbiting the black hole at velocities approaching the speed of light. This material doesn't fall smoothly. Turbulence churns it. Magnetic fields twist through it, and occasionally instabilities form. A clump of gas becomes compressed, heated to millions of degrees by friction and magnetic pressure. This hotspot glows brightly, emitting X-rays and infrared radiation as it orbits. From our perspective, 26,000 light-years away, we see it brighten as it swings into view, then fade as it rotates behind the black hole. The pattern repeats, creating the quasi-periodic eruptions Webb observed. Research shows that hotspots are common in accretion disks around black holes. They have been observed in other galaxies, particularly in active galactic nuclei, where supermassive black holes are feeding voraciously. But Sagittarius A star's disk is faint, sparse, barely there. For hotspots to form, there needs to be enough material to compress and heat. So, where is that material coming from? One possibility is that the black hole recently captured a cloud of gas, perhaps something drifting too close from the surrounding interstellar medium. As this gas spirals inward, it forms temporary structures, hotspots that flare and fade over hours or days. But the hotspot model has a problem. It predicts regularity. If a glowing clump of gas is orbiting the black hole, the time between flares should be consistent, determined by the orbital period. Webb's data showed irregularity. Some flares were separated by 3 hours, others by 6. Some came in bursts, others in isolation. This suggests the hotspots themselves are unstable, forming and dissolving unpredictably, or that multiple hotspots exist simultaneously, their overlapping signals creating a complex pattern. The second major theory invokes magnetic reconnection. Near Sagittarius, A-star magnetic fields thread through the accretion disk and the surrounding corona, a halo of superheated plasma above and below the disk. These fields are stretched and twisted by the motion of ionized gas, storing energy like a wound spring. When the tension becomes too great, the field lines snap and reconnect in a different configuration, releasing enormous amounts of stored energy in an instant. This process is similar to solar flares on the sun, but scaled up by factors of billions. Scientists suggest that magnetic reconnection events are inherently chaotic. They depend on the detailed geometry of the magnetic field, which changes constantly as the disk rotates and turbulence churns the plasma. Predicting when a reconnection event will occur is nearly impossible even with the most sophisticated simulations. This unpredictability matches Webb's observations. The flares come when conditions align, when the magnetic tension reaches a critical threshold. Then they release heating gas to extreme temperatures and producing the infrared glow Webb detected. One compelling piece of evidence for magnetic reconnection comes from the spectral data. Webb measured not just the brightness of the flares, but their color, the distribution of infrared wavelengths. The spectra showed signs of highly ionized gas atoms, stripped of multiple electrons, which requires intense energy. Magnetic reconnection can provide that energy, accelerating particles to relativistic speeds and heating them to temperatures exceeding 10 million degrees. As this gas cools, it radiates an infrared, producing exactly the kind of signal Webb observed. But there's a third possibility, one that's both more dramatic and harder to test: tidal disruption events. Imagine a star, or perhaps a smaller object like a rogue planet or massive asteroid wandering too close to Sagittarius A star. As it approaches tidal forces, the difference in gravitational pull between the near side and the far side of the object become overwhelming. The object stretches, first slightly, then violently. Eventually, it's torn apart, shredded into a stream of plasma that spirals inward, heating as it falls. The result is a bright flare lasting days or weeks as the debris settles into the accretion disk. Tidal disruption events are rare. Astronomers estimate they occur roughly once every 10,000 years per galaxy. But rare doesn't mean impossible. If Webb happened to be observing during one of these events, or if multiple smaller objects were disrupted in quick succession, it could explain the flares. The irregularity would arise naturally from the random timing of objects crossing the danger zone. Some would be larger, producing brighter flares, others smaller, producing fainter ones. The pattern would be chaotic, unpredictable, exactly as observed. Some believe that the galactic center might be more hazardous than we realize. Near Sagittarius A star, the density of stars is high. So is the density of interstellar debris, comets, asteroids, remnants of shattered planets. Gravitational interactions could nudge these objects onto collision courses with the black hole. If this is happening regularly, we might be witnessing not one tidal disruption, but a slow rain of smaller bodies, each one meeting its end in a brief flash of light. Here's where the science becomes speculative but intriguing. Some researchers have proposed that the flares could be related to phenomena even stranger than hotspots or reconnection. One idea involves the ergosphere, a region just outside the event horizon of a rotating black hole, where space-time itself is dragged around by the black hole's spin. In the ergosphere, it's theoretically possible to extract energy from the black hole through a process called the Penrose mechanism. Matter falling into the ergosphere could be split, with one part falling inward and the other being flung outward at high speed, carrying away energy. This process could produce flares, though the details are complex and not yet fully understood. It seems as though the more we learn, the more questions emerge. Each theory explains some features of the data, but leaves others unexplained. Hotspots account for the periodicity, but struggle with the irregularity. Magnetic reconnection explains the chaos, but requires specific magnetic field configurations we can't directly observe. Tidal disruption events are dramatic, but statistically unlikely. And exotic mechanisms like energy extraction from the ergosphere remain largely theoretical, awaiting observational confirmation. One challenge astronomers face is the lack of real-time multi-wavelength observations. Ideally, when Webb detects an infrared flare, other telescopes, Chandra for X-rays, the Very Large Array for radio waves, ALMA for millimeter wavelengths, should all be observing simultaneously. This coordinated approach, called multi-messenger astronomy, allows scientists to see how energy propagates through the system, tracking the flare from its birth in X-rays to its cooling phase in infrared and radio. But scheduling telescope time is competitive. Observatories are in high demand. Coordinating observations across multiple facilities requires planning luck, and often years of proposals and approvals. Research shows that when such coordinated observations do occur, they reveal surprising complexity. In 2019, a campaign involving over a dozen telescopes observed Sagittarius A star continuously for several weeks. They detected multiple flares each, with its own spectral signature and timing. Some flares appeared simultaneously in X-rays and infrared, suggesting a common origin. Others were delayed, the infrared peak occurring hours after the X-ray event, consistent with a cooling cascade. And some flares appeared in one wavelength, but not others, hinting at different physical processes at work. One common misconception is that black holes are cosmic vacuum cleaners sucking up everything nearby. In reality, it's difficult for matter to fall directly into a black hole. Most material has angular momentum, a tendency to orbit rather than fall straight in. To cross the event horizon, that angular momentum must be shed, typically through friction in the accretion disk or interaction with magnetic fields. This process is inefficient. Most of the gas and dust near a black hole never actually falls in. It orbits for a while, perhaps getting heated and ejected, or it drifts away, returning to the interstellar medium. Only a small fraction completes the journey inward. This inefficiency might explain why Sagittarius A star is so quiet. Despite sitting at the center of a galaxy rich with gas and stars, it captures very little. The material that does fall in produces occasional flares, brief moments of brightness. But the black hole never enters the sustained feeding frenzy seen in active galactic nuclei. It's a picky eater. Or perhaps it's simply surrounded by material moving too fast in orbits too stable to easily accrete. Scientists also suggest that the magnetic field configuration near Sagittarius A star plays a crucial role. Magnetic fields can channel material, guiding it onto specific paths. If the field is strong and well organized, It might prevent gas from falling inward, instead funneling it into outflows or jets. Alternatively, if the field is tangled and chaotic, it might enhance accretion by adding turbulence during the disk and allowing material to lose angular momentum more efficiently. Determining which scenario applies requires detailed observations of the magnetic field structure, something that's only recently become possible with instruments like ALMA and the Event Horizon Telescope. One fascinating clue comes from polarization measurements. Light from the region near Sagittarius A star is polarized, meaning its electromagnetic waves oscillate in a preferred direction. This polarization is caused by electrons spiraling through magnetic fields, a process called synchrotron emission. By measuring the degree and orientation of polarization, astronomers can infer the strength and geometry of the magnetic field. Recent observations show that the field near the black hole is complex, with regions of strong organized field and regions of weak tangled field. This patchwork structure could create conditions where reconnection events are frequent, fueling the flares Webb observed. Have you ever wondered whether we might witness something even more extreme? What if a star, not just debris, but a full-size star, wandered too close? The event would be spectacular. The star would be stretched into a tidal tail, a stream of plasma hundreds of millions of kilometers long. As this material spiraled inward, it would heat to billions of degrees, glowing across the entire electromagnetic spectrum. The flare would be visible across the galaxy, perhaps even beyond. And then, over weeks or months, it would fade the last remnants of the star, disappearing across the event horizon. Astronomers call this a tidal disruption event. And while they're rare around Sagittarius A star, they've been observed around other supermassive black holes in distant galaxies. One lesson from studying these theories is that certainty is rare in astrophysics. We can't visit Sagittarius A star. We can't run controlled experiments. We can only observe from afar, collecting photons that have traveled 26,000 years. And from those photons, we try to reconstruct the story. It's detective work, piecing together clues, testing hypotheses, slowly, patiently building a picture of reality. The flares Webb detected are not anomalies in the sense of being unexplainable. They're anomalies because they don't fit neatly into a single framework. They challenge our models. They force us to consider multiple possibilities, to hold competing theories in mind simultaneously, and to accept that the truth might be a combination of several mechanisms, each contributing in different ways at different times. But these theoretical debates don't happen in isolation. The flares, the S-stars, the structure of the accretion disk, they're all part of a larger story. The story of how Sagittarius A star shaped our galaxy, how it influenced the formation of stars, the distribution of gas, the very architecture of the Milky Way. To understand the flares fully, we need to zoom out to see the black hole not as an isolated object, but as the gravitational heart around which an entire galaxy has grown and evolved over billions of years. Every galaxy has a center, but not every center is silent. Not every heart beats the same. Ours, anchored by Sagittarius A star, sits quietly most of the time, a dark throne around which 200 billion stars trace their slow, patient orbits. But it wasn't always this way. There was a time not so long ago, in cosmic terms, when our galactic heart roared, when it fed, when it sent shockwaves rippling through space, carving structures so vast they dwarf entire star clusters. The evidence of that violence still lingers, glowing faintly above and below the galactic plane, waiting for those who know where to look. In 2010, NASA's Fermi Gamma Ray Space Telescope detected something extraordinary. Two enormous bubbles of high-energy radiation, each stretching roughly 25,000 light-years from the galactic center, one extending above the plane of the Milky Way, the other below. They're symmetrical, almost perfectly, so like the wings of some cosmic butterfly. Astronomers call them the Fermi bubbles, and their existence suggests that Sagittarius A star, our quiet black hole, was once anything but. Research shows that these bubbles are filled with gamma rays, the most energetic form of light in the universe. Gamma rays are produced when particles moving at nearly the speed of light collide with gas or magnetic fields. The energy required to fill such vast structures is staggering, equivalent to millions of supernovae exploding simultaneously. The only plausible source is the black hole itself. At some point in the past, perhaps 2 to 4 million years ago, Sagittarius A star underwent a massive outburst. It captured a sudden influx of gas, possibly from a passing molecular cloud, or the tidal disruption of a star. And when it fed, it didn't just absorb that material quietly. It expelled jets of plasma twin beams of particles and radiation shooting outward at relativistic speeds perpendicular to the accretion disk. Scientists suggest that these jets colliding with the interstellar medium inflated the bubbles we see today. The gamma ray emission comes from particles accelerated in the jets, electrons and protons spiraling through magnetic fields radiating as they go. Over millions of years, the outburst ended. The black hole settled back into dormancy. But the bubbles remain glowing faintly, a monument to the galactic center's violent past. One fascinating detail is that the edges of the Fermi bubbles are sharp, well-defined. This suggests the outburst was sudden, a single event, or a series of closely spaced events rather than a gradual process. If the black hole had been feeding continuously over long periods, the bubbles would be more diffuse, their edges blurred by the slow expansion and mixing with surrounding gas. The sharpness tells us something happened quickly. The black hole woke. It fed. And then just as quickly, it went back to sleep. But the Fermi bubbles are not the only evidence of past activity. In 2020, astronomers using the Rosetta X-ray telescope discovered another structure, sometimes called the Rosetta bubbles, overlapping with the Fermi features, but visible in X-ray wavelengths. These bubbles are slightly smaller and show filaments thread-like structures of hot gas aligned with magnetic field lines. The combination of gamma-ray and X-ray data paints a picture of a complex multi-phase outflow with different components cooling and radiating at different energies. It seems as though Sagittarius A star's influence extends far beyond the immediate vicinity of the event horizon. The black hole is the gravitational anchor of the galaxy. Yes, but it's also a sculptor, shaping the distribution of gas, triggering star formation in some regions, quenching it in others. Every star in the Milky Way, including our Sun, orbits this central mass. Our solar system completes one galactic orbit roughly every 230 million years. We're currently about halfway between the galactic center and the outer edge in a relatively quiet region called the Orion Arm. Some believe that supermassive black holes like Sagittarius A star played a crucial role in the formation of galaxies. In the early universe, shortly after the Big Bang, space was filled with hydrogen and helium, the primordial elements forged in the first minutes of cosmic time. Over millions of years, this gas began to clump under its own gravity, forming the first stars and galaxies. But simulations show that without something to regulate, star formation galaxies would convert all their gas into stars far too quickly, leaving no material for later generations. Supermassive black holes provide that regulation. Their outflows and radiation heat the surrounding gas, preventing it from collapsing into stars. This feedback mechanism slows star formation, allowing galaxies to grow over billions of years, rather than burning out in a cosmic flash. Research shows that nearly every large galaxy observed contains a supermassive black hole at its center. And there's a tight correlation between the black hole's mass and the mass of the galaxy's central bulge, the dense concentration of stars near the core. This suggests that black holes and galaxies grow together, influencing each other's evolution. When a galaxy merges with another, their black holes eventually spiral inward and merge as well, creating an even larger black hole and triggering bursts of star formation in the process. Our Milky Way has likely undergone several such mergers in its history. Evidence comes from stellar streams, long ribbons of stars being torn from smaller galaxies as they're consumed by the Milky Way's gravity. The Sagittarius dwarf elliptical galaxy, for instance, is currently being cannibalized, its stars slowly absorbed into our galaxy's halo. Over time, its central black hole, if it has one, will sink toward the galactic center and eventually merge with Sagittarius A star, adding to its mass. One question astronomers are still exploring is how supermassive black holes grew so large so quickly. Observations from the James Webb Space Telescope have revealed black holes with masses exceeding 1 billion solar masses in galaxies less than 1 billion years old, just a few % of the current age of the universe. Growing that massive in such a short time is difficult. Black holes grow by accreting matter, but there are limits to how fast they can feed. Radiation pressure from the infalling material pushes back, creating a natural barrier called the Eddington limit. To exceed this limit, black holes either need to accrete in brief, intense bursts, or they need to have formed from unusually massive seeds. Scientists suggest that some supermassive black holes might have formed directly from the collapse of massive gas clouds in the early universe, bypassing the stellar phase entirely. These so-called direct collapse black holes would start with masses of thousands or even tens of thousands of suns, giving them a head start in the race to become supermassive. Other theories propose that dense star clusters in the early universe facilitated rapid black hole growth through repeated mergers and efficient accretion. Here's something to consider. Sagittarius A star is relatively small for a supermassive black hole. At 4 million solar masses, it's modest compared to giants like the one at the center of M87, which weighs 6.5 billion solar masses, or the one in the quasar TON 618, estimated at 66 billion solar masses. Why is ours so comparatively small? Perhaps the Milky Way formed in a relatively quiet region of the universe with fewer mergers and less available gas. Or perhaps Sagittarius A star has spent most of its existence in a low accretion state, feeding sparingly, growing slowly. One clue comes from studying the orbits of stars in the galactic bulge. By measuring their velocities and distributions, astronomers can reconstruct the Milky Way's merger history. The data suggests that our galaxy experienced a significant collision about 10 billion years ago, when it merged with a smaller galaxy called Gaia Enceladus. This merger likely triggered a burst of star formation and fed gas to the central black hole, causing it to grow and possibly produce outflows similar to the Fermi bubbles, though earlier and on a different scale. It seems as though the history of Sagittarius A star is intimately tied to the history of the Milky Way itself. The black hole didn't just passively sit at the center. It actively shaped the galaxy's evolution, regulating star formation, driving outflows, and perhaps even influencing the distribution of heavy elements. When massive stars near the galactic center explode as supernovae, they enrich the surrounding gas with elements like carbon, oxygen, and iron, the building blocks of planets and life. Outflows from the black hole can distribute these elements across vast distances, seeding regions far from the core, with the materials needed for future star and planet formation. Research shows that the relationship between black holes and their host galaxies is a two-way street. The galaxy provides material for the black hole to feed on. The black hole, in turn, releases energy that affects the galaxy's structure and star formation rate. This feedback loop is one of the most important processes in galaxy evolution. And understanding it requires combining observations across multiple wavelengths, from radio to gamma rays, and across vast scales from the event horizon to the outer edges of the galactic halo. One phenomenon that highlights this interaction is the so-called AGN feedback, where active galactic nuclei, black holes that are actively feeding, inject energy into their surroundings, heating gas, and preventing it from cooling and forming stars. This process is thought to explain why the most massive galaxies in the universe have very low star formation rates, despite containing vast amounts of gas. Their central black holes are so active, so energetic, that they effectively shut down star formation, a process sometimes called quenching. Sagittarius A star, being relatively quiet, doesn't quench star formation in the Milky Way. But its past outbursts, evidenced by the Fermi bubbles, show that it's capable of significant feedback. If it were to enter an active phase again, it could heat gas across large regions of the galaxy, altering the conditions for star formation for millions of years. Have you ever wondered what it would be like if Sagittarius A star were more active, like the black holes and quasars? Quasars are among the brightest objects in the universe, supermassive black holes surrounded by thick accretion disks, shining so brightly they outshine their entire host galaxies. If our black hole became a quasar, the galactic center would blaze with light. The night sky would be dominated by a brilliant point at the heart of the Milky Way's band, visible even through the dust that normally obscures it. Radiation from the black hole would ionize gas across the galaxy, possibly affecting planetary atmospheres, including Earth's. It's a dramatic scenario, but thankfully unlikely. Sagittarius A star lacks the abundant fuel supply needed to sustain quasar-level activity. Scientists also suggest that the black hole's spin plays a role in its influence on the galaxy. A rapidly spinning black hole can extract rotational energy through processes like the Blandford-Zanejac mechanism, converting spin into powerful jets. These jets can extend thousands or even millions of light years, carrying energy far from the black hole and shaping the large-scale structure of the galaxy and its surroundings. Measuring Sagittarius A star's spin is challenging, but ongoing observations of orbiting stars and the accretion disk's properties are providing clues. One humbling realization is that the black hole, massive as it is, represents only a tiny fraction of the galaxy's total mass. The Milky Way contains roughly 1 trillion solar masses of matter, including stars, gas, dust, and dark matter. Sagittarius A star is just 4 million of that. Yet its gravitational influence extends across the entire galaxy. Every star, every planet, every atom is part of a vast, slow dance around that dark center. The Fermi bubbles, the Arosita features the S stars, the accretion disk, they're all pieces of a single story. The story of a black hole that has sat at the heart of our galaxy for billions of years, sometimes sleeping, sometimes stirring, shaping the cosmos around it through gravity and light. And now, thanks to Webb, we're seeing hints that it might be stirring again. The flares, the infrared pulses, could be the early signs of a new active phase, or they could be isolated events, brief flickerings in a long slumber. Only time and continued observation will tell. But understanding Sagittarius A star in isolation is not enough. To truly grasp its significance, we need to compare it with other black holes near and far. We need to see how it fits into the broader population of supermassive black holes across the universe, and what that tells us about the nature of these enigmatic objects and their role in cosmic evolution. Not all black holes are created equal. Some whisper, some scream. Some sit alone in the darkness barely noticed. Others blaze so brightly they can be seen from the edge of the observable universe. To understand Sagittarius A star, to truly grasp what makes it unique, we need to step back and see it in context. We need to meet its cousins near and far, the quiet ones and the hungry ones, the monsters that shape galaxies and the ghosts that wander empty space. Because black holes and all their varieties are not just cosmic oddities, they're storytellers, and every story they tell reveals something fundamental about the universe we inhabit. In April 2019, the world saw something it had never seen before: the Event Horizon Telescope, a global network of radio observatories working together as a single planet-sized instrument, released the first image of a black hole. Not an artist's rendering, not a simulation, but an actual photograph reconstructed from radio waves collected across multiple continents. The black hole was M87 star, the supermassive giant at the center of the galaxy, Messier 87, located 55 million light-years away in the Virgo constellation. And it was enormous. Research shows that M87 star weighs approximately 6.5 billion solar masses, more than 1,500 times the mass of Sagittarius A star. Its event horizon is so large that it could swallow our entire solar system from the Sun out past Pluto, with room to spare. And unlike our quiet black hole, M87 star is ferociously active. It's surrounded by a thick luminous accretion disk, and it shoots a jet of plasma 5,000 light-years into space, a beam of particles traveling at 99.9%, the speed of light powered by the black hole's rotation and magnetic fields. The image showed exactly what general relativity predicted: a dark shadow, the black hole itself surrounded by a bright ring of light, the photon sphere where light orbits the black hole before either escaping or falling inward. The ring glows asymmetrically brighter on one side, because the material in the disk is moving toward us on that side, Doppler boosted by its incredible velocity. It was a triumph of science engineering and international collaboration, and it confirmed what physicists had believed for decades but never directly observed: event horizons are real. Scientists suggest that the difference between Sagittarius A star and M87 star comes down to environment and history. M87 sits at the center of a giant elliptical galaxy in a dense galaxy cluster. It has access to vast amounts of gas stripped from smaller galaxies that ventured too close. This abundant fuel supply keeps M87 star active feeding radiating. Sagittarius A star, by contrast, sits in a quieter neighborhood. The Milky Way is a spiral galaxy in a relatively sparse region of space. There's less gas available, fewer disruptions, less to eat. But there's another category of black hole even more extreme than M87 star: quasars. These are supermassive black holes in the early universe, billions of light-years away, seen as they were when the cosmos was young. Quasars shine with the luminosity of 1 trillion suns, powered by black holes, consuming matter at prodigious rates near or even exceeding the theoretical Eddington limit. They're so bright that they outshine their entire host galaxy's beacons, visible across cosmic distances. One of the most massive quasars known is powered by a black hole in the galaxy TON 618, with an estimated mass of 66 billion solar masses. To put that in perspective, if you could somehow place TON 618's black hole at the center of the Milky Way, its event horizon would extend beyond the orbit of Neptune. It's not just a black hole, it's a cosmic leviathan. And yet, even this giant obeys the same laws of physics as Sagittarius A star. The mathematics is identical, only the scale changes. It seems as though supermassive black holes exist on a continuum, from the quiet dormant ones like ours, to moderately active ones like M87 star, to the blazing quasars in the distant universe. What determines where a black hole falls on this spectrum is primarily its accretion rate, how much material it's consuming. A starving black hole is quiet, a well-fed one is loud. And the loudest ones, the quasars, are likely in their peak feeding phase, gorging on gas from galaxy mergers or other catastrophic events. Research shows that quasars were far more common in the early universe than they are today. In the first few billion years after the Big Bang, galaxies were smaller, closer together, and collisions were frequent. These collisions funneled gas toward galactic centers, feeding the black holes and triggering quasar activity. As the universe expanded and galaxies spread out, collisions became rarer, and most quasars faded, their black holes settling into dormancy as their fuel supplies dwindled. Today, quasars are rare, found mostly in distant galaxies whose light has taken billions of years to reach us. But not all supermassive black holes are in galactic centers. Some wander, These so-called rogue black holes are the result of galaxy mergers, where the central black holes didn't quite merge. Instead, one was ejected, flung out of the galaxy by gravitational interactions destined to drift through intergalactic space. Detecting these wanderers is difficult because they're isolated, surrounded by little gas or stars to make them visible. But occasionally one passes through a gas cloud, accreting briefly and producing a telltale flare. There's also a class of intermediate mass black holes, objects between stellar mass black holes which form from dying stars, and supermassive ones like Sagittarius A star. These intermediate black holes with masses between 100 and 100,000 suns are predicted to exist but remain elusive. They might form in dense star clusters through repeated mergers, or they might be the seeds from which supermassive black holes grow. Observational evidence is scarce, though a few candidates have been identified in globular clusters and dwarf galaxies. One striking example of black hole diversity comes from studying active galactic nuclei, or AGN. These are galaxies with black holes that are feeding actively enough to produce detectable radiation. AGN come in many types classified by their brightness, the wavelengths they emit, and the angle from which we observe them. Some called Seyfert galaxies have moderately active black holes visible in optical and X-ray wavelengths. Others called blazars have jets pointed almost directly at Earth, making them appear extraordinarily bright due to relativistic beaming. Scientists suggest that many of these classifications are not fundamentally different types of objects, but rather the same phenomenon observed from different angles. A quasar viewed edge-on might appear as a Seyfert galaxy. One viewed from the side might look like a radio galaxy with visible jets, and one pointed directly at us becomes a blazar. This unification model simplifies our understanding, suggesting that the diversity we observe is largely a matter of perspective. Here's a question worth pondering. Could Sagittarius A star become a quasar? Theoretically, yes. If a massive gas cloud or even another galaxy collided with the Milky Way, funneling vast amounts of material toward the galactic center, Sagittarius A star could enter an active phase, perhaps even reaching quasar luminosities. But such an event is unlikely in the near future. The closest large galaxy, Andromeda, is on a collision course with the Milky Way, but the merger won't occur for another 4 billion years. And even then, the outcome is uncertain. The black holes might merge, creating an even larger black hole, or they might settle into a binary orbit, slowly spiraling inward over millions of years. Research shows that black hole mergers are among the most energetic events in the universe. When two black holes collide, they release gravitational waves, ripples in space-time, that propagate outward at the speed of light. In 2015, the LIGO Observatory detected gravitational waves for the first time, confirming another prediction of general relativity. The waves came from the merger of two stellar mass black holes, each about 30 times the mass of the Sun, located over 1 billion light-years away. The collision released more energy in a fraction of a second than all the stars in the observable universe combined. Since then, dozens of black hole mergers have been detected, ranging from stellar mass pairs to more massive systems. Future observatories like the space-based LISA mission planned for the 2030s will be sensitive to gravitational waves from supermassive black hole mergers, events that occur when galaxies collide. These observations will provide unprecedented insights into how supermassive black holes grow, how they influence their host galaxies, and how space-time behaves in the most extreme conditions. One aspect of black holes that continues to puzzle scientists is what happens at the singularity. General relativity predicts that all the mass of a black hole is compressed into a point of infinite density, a singularity where space-time curvature becomes infinite, and the known laws of physics break down. But many physicists suspect this is not the true picture. Quantum mechanics. The theory that governs the behavior of particles at the smallest scales should play a role. Combining quantum mechanics with general relativity has proven extraordinarily difficult, but theories like loop quantum gravity and string theory attempt to describe what might exist inside a black hole beyond the event horizon. Some believe that singularities might not exist at all. Instead, quantum effects could prevent infinite density, creating a region of extremely high but finite density, sometimes called a Planck core. Others propose that black holes are connected to other regions of space-time, possibly even other universes, through structures called wormholes. These ideas remain speculative, but they highlight how black holes push us to the frontiers of theoretical physics, where our current understanding reaches its limits. It seems as though every black hole, regardless of size or type, challenges us. They force us to confront the edges of knowledge, the boundaries between the known and the unknown. And in doing so, they reveal not just the nature of gravity and space-time, but the nature of inquiry itself. Science is not about certainty. It's about asking better questions. One common misconception is that black holes are cosmic vacuum cleaners devouring everything nearby. In reality, black holes only affect objects that come very close. At a distance, their gravity is no different from any other mass. If the sun were suddenly replaced by a black hole of the same mass, Earth's orbit wouldn't change. We'd freeze, yes, without sunlight, but we wouldn't be sucked inward. Gravity depends on mass and distance, not on the nature of the object. Another misconception is that nothing can escape a black hole. This is true for anything crossing the event horizon. But outside that boundary, escape is possible, even if difficult. In fact, black holes can lose mass over time through a process called Hawking radiation, named after physicist Stephen Hawking. Quantum effects near the event horizon allow particle-antiparticle pairs to form, with one particle falling into the black hole and the other escaping. Over unimaginably long time scales, this process causes black holes to evaporate, though for supermassive black holes, like Sagittarius A star, the timescale is far longer than the current age of the universe. Research shows that studying black holes across the cosmos, from stellar mass remnants in our own galaxy to supermassive giants billions of light years away, provides a comprehensive picture of how these objects form, grow, and influence their surroundings. Each observation adds a piece to the puzzle. Webb's detection of flares near Sagittarius A star, the Event Horizon Telescope's image of M87 star, LIGO's gravitational wave detections. Together, they weave a narrative of black holes as dynamic, evolving entities deeply connected to the structure and history of the universe. And yet, for all we've learned, mysteries remain. We still don't fully understand how the first supermassive black holes formed so quickly in the early universe. We don't know what happens inside the event horizon. We can't yet reconcile general relativity with quantum mechanics. These gaps in our knowledge are not failures. They're invitations. Opportunities for future discoveries, future telescopes, future minds to explore. But now, after journeying through theory, observation, and cosmic comparison, it's time to return, to come back from the edge of the universe and remember where we started. A flicker of infrared light, a strange pattern detected by Webb, a black hole at the center of our own galaxy quietly breathing, and us watching from a pale blue dot 26,000 light years away, trying to understand what it all means. We've traveled far tonight, 26,000 light years through dust and darkness, through twisted space-time and magnetic storms to the heart of our galaxy. We've watched stars dance at the edge of oblivion. We've seen light born from darkness, heard whispers from a place where time itself bends. And now, it's time to drift back to this quiet moment, back to Earth, back to the simple, profound fact that we are here alive, aware, able to wonder about black holes and infrared flares and the nature of existence itself. Sagittarius A star sits at the center of everything we know, 4 million solar masses, an event horizon 17 times wider than our sun, A gravitational anchor around which 200 billion stars orbit, including the one that warms this small planet where you sit, breathing, listening. For most of human history, we didn't know it was there. Our ancestors looked up at the Milky Way's bright band and saw only mystery, a river of light with no explanation. They told stories about it, gods, spirits, roads to the afterlife. They were not wrong to see it as sacred. They simply lacked the tools to measure what their intuition already sensed, that the center holds something profound. Research shows that humanity's understanding of black holes is less than a century old. Einstein published his theory of general relativity in 1915. The term black hole wasn't coined until 1967. The first image of one appeared in 2019. And Webb's detection of strange flares near Sagittarius A star happened just recently in our own lifetimes. We are living through the golden age of black hole astronomy, witnessing discoveries that will be studied for generations. What we're learning now will be in textbooks 100 years from today, taught to students who will look back at our time and marvel at how much we didn't yet know. But here's what strikes me most. It's not the black hole's size or its gravity or even the physics unfolding near the event horizon. It's the connection. The fact that we beings made of atoms forged in stars, powered by chemical reactions, experiencing consciousness for a brief flicker of cosmic time, can point instruments at the sky and understand what's happening 26,000 light years away. We can measure the mass of an invisible object. We can track stars orbiting at 2% the speed of light. We can detect infrared flares lasting hours and piece together theories about magnetic reconnection and tidal disruption. That ability, that capacity for knowledge, is as wondrous as the black hole itself. Scientists suggest that curiosity is not a luxury. It's fundamental to what makes us human. We don't study black holes because they're useful. Though the technology developed along the way, gravitational wave detectors, adaptive optics, supercomputers, often finds unexpected applications. We study them because we want to know, because the universe is vast and strange and beautiful, and we are part of it, and understanding it helps us understand ourselves. Every photon web detected from Sagittarius A star began its journey long before humans existed in our current form. 26,000 years ago, our ancestors were hunter-gatherers, living in small groups, making tools from stone and bone painting on cave walls. They had no concept of galaxies or black holes or space-time. And yet they looked up. They wondered. They told stories about the lights in the sky, trying to make sense of the cosmos with the knowledge they had. We are their descendants, and we're still looking up, still wondering, still telling stories. The tools have changed, the questions have gotten more precise, but the impulse, the deep human need to understand, remains the same. It seems as though the flares Webb detected are just the beginning. Sagittarius A star is being watched now more closely than ever before. Multiple observatories are coordinating efforts, combining data across wavelengths, tracking every flicker and variation. The Event Horizon Telescope is working on new images, higher resolution, more detail. Future missions, like the proposed Black Hole Explorer, or BHEX, aim to create even sharper pictures, perhaps revealing the structure of the accretion disk, the dynamics of the magnetic fields, the processes happening just outside the event horizon. We're going to learn more. The mystery will deepen before it resolves. And that's as it should be. One thing Webb's discovery reminds us is that the universe is not static. It changes. Slowly, yes, on time scales that dwarf human lifespans. But it changes. Sagittarius A star was once more active. It might become active again. Stars will continue falling inward. Gas will drift closer. The black hole will feed flare, and eventually, perhaps millions of years from now, merge with another black hole when the Milky Way collides with Andromeda. The universe is in motion, always has been, always will be. And what about us? What role do we play in this cosmic story? We're observers, yes, but we're also participants. We're made of the same elements that swirl in the accretion disk. Carbon, oxygen, nitrogen, iron, all forged in stars that lived and died billions of years ago. Those stars were orbiting Sagittarius A star, just as our sun does now. The atoms in your body have been on a journey as long and complex as the galaxy itself. You are quite literally stardust, shaped by gravity and time into something that can think, feel, and contemplate black holes. Have you ever stopped to consider how improbable this is? Not just that you exist, though that in itself is extraordinary, but that you exist in a moment when technology allows you to see the galactic center. 100 years ago, this conversation would have been impossible. 100 years from now, who knows what we'll have learned? You're here now in this brief window where the universe is revealing its secrets and you have the tools to understand them. That's not luck, that's timing, and it's precious. Research shows that the more we learn about the universe, the more questions we uncover. For every answer, 10 new mysteries emerge. We thought we understood gravity until we discovered dark matter, an invisible substance that outweighs all the stars and gas in the universe. We thought we understood the expansion of the cosmos until we discovered dark energy, a mysterious force accelerating that expansion. Black holes, too, hold secrets we're only beginning to glimpse. What happens inside the event horizon? How does quantum mechanics reconcile with general relativity? Are there other forms of black holes we haven't yet imagined? These questions don't frustrate scientists, they energize them. Because science is not about having all the answers. It's about refining the questions, building better tools, and slowly, patiently expanding the sphere of what we know. Every observation, every experiment, every late night spent analyzing data adds a tiny piece to the puzzle. And collectively, over decades and centuries, those pieces form a picture. Incomplete, yes, always incomplete, but beautiful nonetheless. Here's what I want you to carry with you as you drift towards sleep. You live on a planet orbiting a star in a galaxy that revolves around a supermassive black hole. That black hole is not just a scientific curiosity. It's the reason the galaxy has the shape. It does the reason stars formed, where they did the reason our solar system exists in a stable region, with enough heavy elements to build rocky planets and eventually life. Sagittarius A star is part of your origin story. And now, thanks to telescopes like Webb, you can see it. Not with your eyes, but with instruments that extend your senses across unimaginable distances. You can witness the universe not as it is, but as it was light from the past arriving in your present, carrying information across the void. Scientists also suggest that the act of observing changes us as much as it reveals the cosmos. When you learn that time slows near a black hole, it shifts your perspective on time itself. When you see an image of an event horizon, a boundary beyond which nothing returns, it makes you think about boundaries in your own life, the points of no return we all face. Science is not separate from human experience. It's deeply woven into it, shaping how we see ourselves and our place in the universe. The flares Webb detected will continue to be studied. Papers will be published, conferences will debate the findings, new theories will be proposed, tested, refined, or discarded. And through it all, Sagittarius A star will continue its slow, patient existence, feeding occasionally, flickering briefly, governing the motion of stars for eons to come. It doesn't care that we're watching. It doesn't know we exist, but we do, and that matters. One final thought. The universe is vast, yes. Almost incomprehensibly so. But it's not indifferent. It follows rules, patterns, laws that we can discover and understand. Gravity pulls, light bends, energy is conserved. These laws apply everywhere, from the event horizon of a black hole to the cells in your body. We are not separate from the cosmos. We are expressions of it. The same forces that shape galaxies shaped you. And in understanding those forces, you're participating in the universe's ongoing effort to know itself. So, as you close your eyes tonight, imagine this. Somewhere far above, light is leaving the galactic center. infrared photons carrying heat from gas spiraling towards Sagittarius A star. They'll travel for 26,000 years, crossing the void until they reach Earth and strike a detector. Maybe that detector hasn't been built yet. Maybe it will be built by someone inspired by tonight's story. Maybe that someone is you. The universe is patient. It waits. It reveals itself slowly to those who look carefully and listen closely. And every now and then, it flickers. A black hole breathes. A telescope notices. And we here on this pale blue dot get to be part of the conversation. Thank you for drifting with me tonight, for letting curiosity guide you through the darkness, for wondering about black holes and galaxies and the strange, beautiful universe we call home. If this journey brought you peace or sparked a question, or simply helped you see the night sky a little differently, then it was worth every word. There are more stories waiting, more mysteries to explore, more quiet nights where science and wonder meet. Until then, rest easy. Dream of light born from darkness. Dream of stars dancing on the edge of forever. Dream of a universe that for all its vastness made space for you. Sleep well. Good night.